having discussed the case of infinite string, okay, the next obvious step is to increase the complexity by introducing a boundary condition. Okay, so that we will do, and but generally I don't jump a very long step. What we will do, we will take a very short step, that we will introduce the boundary condition only on one side. Okay, so keep these pictures in mind so that we can compare later on. So here is what is happening now. So you have the string here, but it extends on one side to infinity, but on the other side it's stuck. Okay. Now what will happen in this case? How do you get, or what will be the general solution of a wave propagation on this condition? Now, if you follow the same argument, you could write, y of xt is equal to that f of x minus ct plus f of x plus ct. But then why it won't work there? The reason is, if you see at t equal to 0, at x is equal to 0, which is this condition, say x is increasing from here, so this point is x is equal to 0. So if you put x is equal to 0, this becomes f minus ct plus f ct, right? That will not be 0 for all time to come. So that means this kind of a situation definitely won't work. So what should work? Let's say we have this condition that minus of f of x minus ct plus f of minus x minus ct. This equality is, so y xt is equal to this. So I'll just say that this won't work. Okay, so this won't work. So we have to have this kind of a situation. Now, why this will happen? Because see, if now I put x is equal to 0, I get minus f of minus ct plus f of minus ct. This is 0. Okay. Now, what exactly or how you should visualize this solution? So now I can say that this is a solution of my wave equation with one end fixed, rigidly fixed. Okay. Let's see what exactly does that mean. So y of x of t is your minus of f of x minus ct plus f of minus x minus ct. Think about it. Say at say t is equal to at t is equal to say 5 seconds, this wave is somewhere. Okay, and best thing is, try to imagine that this fz Okay, whatever is the argument. Suppose you have the fz is a function whose argument is z, and this is the function which is or I would say even like this only, I should say, okay, like that. At x is equal to 0, it has a peak and it tapers down there. Okay, suppose fz is such a function, and at x equal to 0 this happens. Now at t is equal to 5 seconds, where the peak will be, so at this part I am talking about, if this part its peak will be at 5c, right? See, fz is a function whose peak happens at, sorry, z here, when its argument is 0. Now I am considering at time t equal to 5 seconds. So this part is 5c, sorry, okay. I was actually trying to see a time earlier to that, so minus 5 seconds, sorry for that, okay. Before the time actually started, imagine where it was, so then we will come to 0 and then we will move forward. At minus 5 second, it will be at 5c, right? Because, yeah, so this becomes plus, so yeah. But then at t equal to minus 1 second, this will be at 1c. So that means this part is moving again this side only with speed c. Okay. And then it's one other way to see this is nothing but f of minus x plus ct. So any function with x plus ct moves leftward. So that's another way. But anyway, now there is a reason why this and this are there. Now, what happens to this? This moves right way, but there is a can you imagine what this minus is doing and what this minus is doing? See, this minus flips about x-axis, this minus flips about y-axis, right? So that means if I have, that's clear, right? So now if I have a situation like this, that before the time actually started, what I'll do, I'll draw from here so that here is our 0 position. Now here you try to imagine that there is an imaginary string, okay, on which things can move like the way they move on the physical strings. Okay. Now think that when t was before even t equal to 0, this kind of wave was coming from that side. Say, let me draw something like this maybe. That was, say, f of minus z. Now here, and then this was coming this side, and from here, say it was coming exactly, so it will be once flipped this side and once flipped this side, right? So exactly the same distance, and so something like that. And this moves like this. So this one is minus f of x minus ct, and this one is plus f of minus x minus ct. Okay. Now as they reach this point, so what will happen is at every such moment they will cancel out each other, right? And I want to draw it, but I don't know whether I have the skill to draw it. Say a certain time here, like this, and at that time this was here somewhere, like that. So, but if whatever may be the time, at this location they cancel out each other, okay, and after certain time this one will come here and this one will just vanish in this form, like that. Okay, so let me say draw times, say this is say t is equal to minus 5 seconds, so this is say t is equal to minus 1 second, not minus 1 because this has already entered the physical domain, so I'll put say just for fun, nothing else. It could be t equal to minus 1, doesn't matter, but I'll not put that. Say I'll put plus 1 second, and this is t is equal to say 5 seconds. So when t equal to 5 seconds happens, so this is actually the exactly opposite thing is there. Now the same thing it is written in another way, you know, that at the rigid end the wave gets reflected back with a phase transition. This you have studied, I think, in your 12th standard also, that when a wave comes, a rigid end, it meets a rigid end, it gets flipped and goes back, right? So the same thing, this is another way to look at it which will be helpful in evaluating things. That is helpful in imagining or visualizing. This is helpful in doing maths, but both are same. Now why does it, in fact, you know, why the phase transition happens? So this picture will tell you why that thing happens. That, see, something was coming here with a positive amplitude. The job of this rigid end is to pull it back so that it will be 0, right? Now to do that, it has to apply a force, and in doing that, yes, the other thing is pulled back, the reaction force, and it goes down. So that's how in pulling that and getting a pull from the thing, because the string pulls the peg pulls the string. Because this, when this comes, because of the tension, that the string first tries to pull it, right, the peg, and as a reaction the peg will pull in the opposite direction, and because there is inertia, so it will move downwards because of that pull. Okay, and that's what happens, and the shape completely gets reversed, and so those are the two things which manifest them, you know. One is reflection and one is the phase transformation. So this is the reflection and this is that phase transition of 180 degree. Whatever was positive will become negative, to keep things 0 at that for any time to come. Now why did I say that it will be useful for calculation? Because now you can actually calculate, given any shape for initial velocity and initial condition, you can actually calculate that, and that I'll just note down, but then you can code it to see. So if you have now y naught x and v naught x the way we had in the previous case. You define Sz the way we did. Then what you do, you have to now define a function, say h, okay, or yeah, okay, h to be y naught of z, half, I'll write it other time, means in the final equation. So just define like this for z greater than 0, because now you can't define an initial condition for when x is less than 0, or that means for z less than 0 you can't do it. Z is, okay, I'll write it here, z is nothing but x plus or minus ct, right? We are going to replace z with that. But then because t is changing, so z can sometime move to negative, but we don't have initial conditions, we can't define there. So that is why we are doing this. So this one will be, say, minus y naught of minus z for z less than 0. So this is what your function of h of z. Similarly, you can put, say, a q of z in terms of s. Okay, so that is, say, s of z when z is greater than 0, and s of minus z when z is less than 0. Okay, now if, and then your y of x and t will be the usual way, half I am taking out. So now you know what this half means and from where it comes, and then you have, h of now z you can replace with this, so x minus ct plus h x plus ct minus 1 over c q x minus ct plus 1 over c q x plus ct. So that's what will be the solution to your differential equation, the wave equation which we named. And when there is one, or you can say semi-infinite string, one side is fixed, the other side is extending to infinity, and then you are applying a particular sort of initial conditions. So now you can have any of these initial conditions and you can solve for the equation. Okay. Now again in this case, I would like you to write the MATLAB codes to plot these functions as function of both x and t, where you can give any initial conditions to start with, both displacement and velocity initial conditions. Okay. So if we try to, it's difficult, just we can try once, at least for the displacement. Suppose you have this is the condition string, and here you have the peg, and yeah, like this imaginary string, and say you have this to be the initial condition, y naught x. Try to draw what will happen and how to visualize the equations which we wrote. Now if you go back here, so this we have to first define hz, right? So that means, and then this half also will be multiplied with that. So let's see how they will look like. So this half, I'll increase this height a bit, otherwise half will be very small. So this is maybe the initial one. Now our half things will be just here. One part is this. So this is which portion? This is this. For z greater than 0 you have defined it, y naught z, and then this part. You have to first flip it, so it will come somewhere here, the same distance maybe, and it will be flipped the other side also, and yeah. So this is, so this one is minus f, not f, y naught, no? Y naught minus of x minus ct, right? Minus z, and it's moving this side, and this one is your y naught y naught of x I think something
minus x minus.
Okay, this is that. Okay, forget it. I'll have to change this because, yeah, this is this part, x minus ct. So this this portion, this part is coming here, this portion, and now this side is the other one. It's minus, I mean, it makes, just try to, I'm just trying to be consistent with the previous equation. So that is why, I mean, this is minus and this is minus of minus being plus. So please you understand that. And this is minus of x minus ct. I mean, ideally I would have written this plus and this minus, but the way I wrote the previous equation, to be consistent with this, these are the things. So this one moves in this direction, this moves in this direction. So then once they meet each other, they coalesce and things happen the way we explained.
Sir, but the red one is the shape at t is equal to 0, right?
Yep. Okay. Just a minute, So what is the problem? Oh, thank you. Let's see what we have made the mistake. We have drawn only one part. See, this hz has both the components, right? So, sorry, thank you for that. Now this full thing I should have drawn with a single color. This one, then it comes here and it goes here like this. So this is a single one. So please correct it. So this is a single function which basically is this h and half of that. Okay, and the other half will be, exactly opposite of that. To start with, they will start exactly the same point. Okay, how do I draw the blue? So okay, that's fine. So they will look exactly the same to start with. Again the same thing. So both of them are sitting at the same location to start with, but the moving directions are different. So whatever I had written, that could be there. But thanks for the doubt. Otherwise, x minus ct moves this way. Is it now fine? Good, thanks. So, okay, we will stop here, and then your job is to now write the code for this and submit it so that we can have in our repository, and then we should see them happening. Okay, see you in the next segment.